Good morning all of you. So any clarifications on integral methods? I think I have been going a little bit slow in the last 2-3 classes, so takes enough time for you to understand what I had been doing. So last class we had looked into the approximate solution for flow with pressure gradient, the Falkner-Skan method, and applied that to heat transfer problem. And finally we also looked into an approximation to the Karman-Pohlhausen solution. Okay, the ordinary differential equation can be simplified and directly integrated by what is called as the Wahl's approximation. Okay, so there he has plotted h of k as a function of k and found that is a very linear curve, and he has given the approximate profile for the linear curve, and that's what if you use it becomes much straightforward to integrate the equation to get the momentum thickness. Okay, so once you get the momentum thickness, from there you can get your other thicknesses like displacement thickness and boundary layer thickness, which are required to calculate the average flow properties like skin friction coefficient. And the same way you can solve the heat transfer problem, and in the heat transfer problem you will get an ordinary differential equation for zeta, which is the ratio of your thermal boundary layer thickness to momentum boundary layer thickness. Once you have the expression for momentum boundary layer thickness, so therefore you can calculate your average integral heat transfer quantities like heat transfer coefficient, and therefore you can get the expressions for Nusselt number. Okay, so this is the standard procedure for all the solutions, whether it is similarity solution or integral solution. This is the standard procedure. In the integral solution you guess a profile, you approximate the velocity profile and temperature profile, and from there you calculate your boundary layer thickness and thermal momentum and the thermal boundary layer thickness. Okay, whereas in the case of similarity solution you have to solve the ordinary differential equation numerically by some shooting technique or whatever and get the curvature at the wall, and from there you can get the other properties such as skin friction coefficient, and also you can get your boundary layer thickness and other thicknesses, and for heat transfer you can also get the slope of the temperature profile at the wall, and from there you can calculate your expression for heat transfer coefficient and Nusselt number. Okay, so what we will do today, so we had so far looked at application of integral techniques for flows without pressure gradient, that is the similar to the Blasius similarity solution. We approximated that with the integral method, and also we extended that to flows including the pressure gradient terms, that is like the Falkner-Skan similarity solution. We can apply the integral methods for a similar problem for a wedge with different wedge angles, and we can derive approximate solutions for these. Okay, we had also looked at the case of circular cylinder, okay, which is a limiting case, which is a stagnation flow, and also the heat transfer for flow past the circular cylinder. Now we will look at a case where you can consider a simpler case or maybe even the wedge, but we will take a simpler case, that is the flow past a flat plate. However, the boundary condition here need not be a uniform wall temperature or uniform heat flux. Okay, so most of the real cases you will find that the temperatures are actually varying along the surface. Okay, so if you want to consider non-uniform temperature or non-uniform heat flux, so how do we solve such kind of problems? Okay, we do not have a straightforward similarity solution to such kind of problems, but it is quite likely that we can develop a similarity solution for a particular case where your variation is predetermined, that is if you have a flat plate and your variation of the wall temperature is something like a power law x power m variation, okay, where m is some real number, and so this is a power law kind of a profile. So for this you can develop a similarity solution also. Okay, we can also very easily solve this by integral methods, which we will see now, and it need not be a variation like this, it can be any kind of variation. Okay, that is the advantage of the approximate methods. Okay, the approximate method give you a lot of flexibility in approaching problems with different kinds of boundary conditions, and also things like where the boundary condition there is an unheated starting length. Okay, so there is no similarity solution if you have an unheated starting length. So these kind of problems with the variation in the boundary temperature and the heat flux can be easily solved using the approximate solution. Okay, so today we will look at extending the simpler approximate solutions to a case where you have more complicated boundary conditions. So the first case we are going to do is non-uniform surface temperatures. Okay, so here you can consider flat plate where your temperature is varying in an arbitrary manner, okay, and of course you have your free stream velocity and free stream temperature, and we will look at a particular technique called the Duhamel superposition method for solving this problem. Okay, so the specified condition is something like this. You can maintain locations where you want to specify a particular wall temperature. For example, let us call this as zeta. At the location zeta equal to 0, you start with some specified temperature. Okay, that could be something like a T wall 1. So let me draw how the wall temperature profile will look. So this is my plot of T wall, of course as a function of my position. So at this particular location zeta equal to 0, I will have, for example, a piecewise constant value of wall temperature which is T wall 1. Okay, so this is existing till a value of zeta which is equal to zeta 1. Okay, so like this I will have multiple piecewise constant values of surface temperature. Okay, so this is a simpler case to begin with. Of course your actual variation need not be piecewise constants, it can be a gradual variation, smooth continuous variation. Okay, so like this we can look at temperatures which are successively increasing, the wall temperatures which are successfully increasing in a piecewise constant manner. Okay, so like that you can go up to some value of finally zeta n. Alright, so this is how your surface temperature is now plotted as a increasingly a piecewise constant which is increasing. Okay, so this is like an approximation to a profile which is like this. Suppose your wall temperature profile was this, the basic approximation for this is to assume piecewise constants. You break this continuous curve into piecewise constants, okay, and you have an increasing trend in the wall temperature. Okay, so for this how do we approach the problem? Okay, thankfully the equation that we are solving, the energy equation is linear once you know the corresponding velocity profiles. So the velocity profiles are not going to get affected as long as your properties are not affected by the temperature. Okay, so in that case your velocity is decoupled from the temperature and you can plug in the particular value of velocity at a location into the energy equation and your energy equation becomes quasi linear, and therefore for any linear partial differential equation, if you have varying boundary conditions, okay, you can break the solution into multiple solutions and superpose the solutions for each boundary conditions linearly. Okay, so the resulting solution is a linear combination or linear superposition of multiple solutions, each corresponding to a different boundary condition. Okay, so if you solve by method of separation of variables, you will know that for example the heat conduction problem, okay, the method of separation of variables will work if you have for example homogeneous boundary conditions in 3 directions and 1 non-homogeneous boundary condition. Okay, for example in conduction case you will maintain this at some high temperature and the remaining 3 sites, or maybe you can assume that or you can non-dimensionalize the temperature in such a way that the non-dimensional temperature is 0. Okay, for this you can solve the conduction equation, 2D conduction equation by means of separation of variables. Okay, so there will be an eigenvalue problem in this direction, basically where you have 2 homogeneous boundary conditions. In the other direction you apply the remaining homogeneous boundary condition, and finally whatever non-homogeneous boundary condition is there to get the final constants. Okay, but if you have non-homogeneous boundary conditions on all the 4 sides, so how do you solve this problem? You can still solve it by separation of variables, but you need eigenvalue problems. Okay, for eigenvalue problems you need homogeneous boundary condition in a particular direction. So to do that, if suppose these were non-zero, okay, this was something like TC1, TC2 and TC3 which were not 0. Okay, so you can break this into problem where you have TH here and you can put TC1 here, TC3 and 0. Okay, or what you can, if you want to make it completely homogeneous, you can break this as 3 zeros here, plus you can make the other 3 as zeros, and you can make this as TC1 plus, of course you can make these 3 as zeros, and this is your TC3 plus this is your TC2 and the other 3 zeros. So you can apply eigenvalue problems in different directions. In this case you have y direction, you have x direction here, in this case you have the x direction. Okay, so you create 4 equivalent eigenvalue problems and you get solutions for each of these case, okay, with one non-homogeneous boundary condition, and finally you superpose all these 4 solutions and that will give you the solution for this problem. Okay, this can happen only if the partial differential equation is linear and conduction equation is linear, right. So the same way, if you look at the convective heat transfer, the energy equation governing convective heat transfer, that is also linear. So therefore if you have a combination of multiple boundary conditions like this, you can superpose solutions where you have, for example, you have multiple wall temperatures, you can solve one problem where you have T wall 1 throughout, okay, and the solution to that is known, plus you have another problem where from zeta equal to zeta 1 to the end you have T wall 1 minus T wall 2 or T wall 2 minus T wall 1, okay, that is the delta T wall. So that is applied to the entire plate, and again you know the solution for that, and from zeta equal to zeta 2 till the end, so that is you have T wall 3 minus T wall 2. So like that you keep on applying successive delta and you apply that as your boundary condition and you solve the problem. Now if you do that, you have individual solutions where you have an unheated starting length and then the rest of the plate where you have a uniform temperature. Okay, so like that you break up the problem into multiple boundary conditions and then you get the solutions, you already have the solution, so you add them, you superpose all the solutions together and that will give you the solution for this problem. Okay, that is why it is called as a superposition method. Okay, so this is also called the Duhamel method. So let me indicate this as T wall 2, this is T wall 3, T wall 4 and so on. So this is your T wall n minus 1. Okay, okay, let me call this as T wall n. Okay, so the solution for these is, anyway you have to solve the energy equation. Boundary conditions are now at y equal to 0, you do not have a constant value of temperature but T equal to T wall, which is a function of x, okay, and the other boundary conditions are the same. y going to infinity t is equal to t infinity, and at x is equal to 0. Okay, now following some analogy similar to the conduction problem, where also the partial differential equation is linear, and you can convert the problem into equivalent 4 equivalent problems with convenient boundary conditions. So you can do the same way here also, and you can superpose the solution. So therefore the solution for this problem will be something like, you can take one problem like this, where you have your free stream temperature T infinity, okay, and this is your starting from your zeta equal to 0, entire plate you maintain at temperature T wall 1, right. So this is your first problem, and already you have the solution, uniformly heated plate, right, from without any unheated starting length, okay. So the if you non-dimensionalize the temperature, your solution to be found out will be in the form phi for the case zeta equal to 0, and it is a function of x and y, will be t minus t infinity by t wall 1 minus t infinity. This is the way I am going to non-dimensionalize, okay. So, and how does the corresponding wall temperature, the non-dimensional temperature profile look at the wall? If I plot this phi at zeta equal to 0 x comma y equal to 0, so I am plotting the temperature at the wall, so this will become T wall 1, okay, and throughout it is T wall 1, okay. So therefore it will be just 1 everywhere, alright. So this is one case. Now I can break it up into multiple problems, okay. My second problem will be what? So now I have solved one problem where everywhere it is T wall 1, but now you can see from zeta equal to zeta 1 to zeta 2 it is T wall 2. So now what is the next problem that I have to solve? Okay, so to do that, what should I do? Now I should not solve for any heat transfer problem till zeta 1, because I already have solved it here, okay. So I should maintain what is something called as the unheated starting length till zeta 1, right. And what should be the free stream velocity that I should take, so that there will not be any heat transfer here? Now this is already at T wall 1, okay. So I have to choose a free stream velocity such that there will not be any heat transfer, so that this remains unheated. So what is that free stream velocity that I have to take? I cannot take T infinity. If I take T infinity, the T infinity is different from T wall 1. T wall 2 minus T wall 1. Why? It should be T wall 1, okay. So if I take a free stream which is at T wall 1, so this is also at T wall 1, so therefore there will not be any heat transfer till here. Now at this point onwards this will be at T wall 2 till zeta 2, okay. So now I can introduce another non-dimensional phi corresponding to zeta equal to zeta 1 onwards, okay. Now how do I non-dimensionalize this? T minus T wall 1 by T wall 2 minus T wall 1, exactly, okay. So if you draw the non-dimensional profile at the wall versus x, how does it look? Now initially till zeta 1 there will not be any heat transfer, so from here it will start and this will be 1 throughout, so this will be a T wall 2 throughout, okay. So that means here this portion is now T wall 1, this entire portion is T wall 2, okay. So now you are solving for T wall 2 minus T wall 1, that is the difference that you are solving, okay. So that means now you have solved for Twal1 here, now here you have already solved for Twal1 plus Twal2 minus Twal1, so that is basically as Twal2. Now same way you have to break this into problems depending on the number of piecewise constants that you have, alright. So now if you extend this to, I will just give you a representation for the third one. So this plus this plus okay, so till zeta equal, from zeta equal to 0 to zeta equal to zeta 1 you have Twal1, okay. Now from zeta equal to up to zeta 2 you have Twal2. Now you have to maintain Twal3 throughout, okay. So to do this again we assume a free stream velocity where you are maintaining everywhere as now Twal2 and your free stream, not everywhere, I am sorry, from zeta equal to 0 to zeta equal to zeta 2 as Twal2 and your free stream velocity is now Twal2. From zeta 2 onwards it will be Twal3, so you maintain everywhere as Twal3 and you define your phi as zeta equal to zeta 2 comma x comma y, which is equal to T minus Twal2 by Twal3 minus Twal2. So if you plot again phi at y equal to 0 as a function of x, okay, so till your zeta equal to zeta 2 there is no heat transfer, from here it becomes 1. Okay, so this is how you get different solutions. Okay, now you have actually solved here for the remainder Twal3 minus Twal2 for this particular region. Okay, so already you had solved for Twal2 minus Twal1 and also for Twal1 minus T infinity. So finally that will be Twal3 minus T infinity. Okay, so then you can superpose all these solutions together. Yes.
But there will be heat transfer in zeta to 0, zeta at 0 to zeta is equal to 1 because temperature is different from the wall temperature.
Yeah, so you have to maintain this at Twal2 throughout because you have already solved for this till here. You are not interested in this region. Okay, so you maintain this entire region at Twal2 and then this will be from Twal3. So here also you have already solved here. Okay, so you do not need any solution, the solution is already there, that is this solution. Till this region you already have solution from this, so you do not have to solve for anything here. So you maintain a unheated starting length forcibly by maintaining the free stream temperature and this the same way here. Okay, so you already have solved from here to here, so you maintain a same temperature equal to the free stream temperature so that there is no heated length. Okay, so therefore you define your phi in generic terms as T minus T wall zeta n minus 1 by T wall zeta n minus T wall zeta n minus 1. This is your generic formula for defining your non-dimensional phi. Okay, so where for example if n equal to 1, so that is basically that is your zeta 0, that is this first case. Okay, n equal to 2, that is your second case, n equal to 3 will be this particular case. Okay, so this is a generic formula how you are defining your non-dimensional temperature. Okay, and the non-dimensional form of the energy equation will be u d phi by dx plus at y equal to 0. Now what will be the value of phi? Now till your x is greater than 0, or maybe you can say if you want to write it in generic terms, zeta n minus 1 to zeta n. Okay, so this should be what, 0, and for x greater than yeah, so for x greater than or equal to zeta n, it should be 1. Okay, can you just check that? It has to be eta n minus 2 minus 1, is that right? Okay, so when you start with of course something negative, it means it is, you can say, free stream. Okay, free stream, so there it will be 0, and then when you start with n equal to 1, so up to, for this case, so up to eta 0, basically you do not have any heat transfer. From here onwards you have greater than that, you have your phi equal to 1. Okay, so this is your generic solution. Okay, and this is your generic way of non-dimensionalizing phi. Now therefore the solution to the problem for temperature T minus T infinity, so this is what we finally want to find out. So now we have broken this into sub problems, and for each already we have the solution. Okay, we have the unheated starting length problem. Okay, so we can just combine all these. For the case where your zeta equal to 0, how do we express T minus T infinity? T minus T infinity is phi zeta equal to 0 times T wall 1 minus T infinity. Okay, so this is T wall 1 minus T infinity into phi zeta equal to 0 x comma y. Okay, plus the next problem will be T minus T wall 1, which is T wall 2 minus T wall 1 into phi zeta equal to zeta 1 x comma y, plus all the way till T wall eta n minus T wall eta n minus 1 phi eta n x comma y. So that is your final this thing. Okay, so T wall eta n minus T wall eta n minus 1, that is the last this thing. Okay, so you keep adding up all these solutions such a way that finally if you add up you get the solution to the problem where you have variation like this in the boundary condition. Okay, so already we have the solution to phi. Phi is what? T minus, you can look at this, T minus T infinity by T wall minus T infinity. So what is, suppose if you assume a cubic temperature profile, so what is the, how can we write phi? Suppose you assume cubic temperature profile, you non-dimensionalize it, y 1 minus, correct, what you have said is correct, but why 1 minus? What you are saying is correct, but it should be 1 minus.
1 minus.
Why it should be 1 minus? Signs have changed, no. How did we define the non-dimensional temperature theta when we were fitting a cubic profile? T minus T wall by T infinity minus T wall. So my phi is what? So that should be 1 minus theta, right? So therefore what it should be 1 minus 3 by 2 y by delta t plus 1 by 2 y by delta t the whole cube, correct. So this is the profile satisfying the condition x greater than or equal to zeta n minus 1, right. So this is the corresponding wall temperature, so uniform wall temperature, correct. Corresponding to that, this is the profile in the boundary layer, thermal boundary layer. Now I already know the solution, so only thing I have to now linearly combine all the solutions, that is all. And how do you check that, how do you know that this is the correct solution, correct for way of superposing the solutions? How do you verify that? The simplest verification is getting the boundary condition itself. So you apply this at y equal to 0, what it will be now until, so this profile will be 1 everywhere, okay. So this will be t wall 1 minus t infinity, okay. Suppose you want to check that at between zeta equal to zeta 1 to zeta 2, that this gives me t wall 2 minus t infinity, does it give? That is the check, right. So this is t wall 2 minus t wall 1, and this is 0 before and it is 1 between zeta equal to 1, zeta 1 and zeta 2, and the other things are all 0, okay. So t wall 1 cancel, so this is t wall 2 minus t infinity. So this retrieves my boundary condition, okay. This is a good check that, therefore this is the correct solution, because your boundary condition also is a part of the solution, right. So this is the, therefore how you have to write it, and if you check if the wall boundary condition are retrieved, then let me call this as equation number 1, okay. Then 1 is correct, okay, or 1 is represented correctly, okay. So now that is it. Once we write the solution like this is valid if you have a piecewise constant variation. In the actual case the variation should be continuous, so instead of having a summation of piecewise constants, we can replace that by an integral which represents a continuous summation, okay. So that is what we are going to do now. So I would like to, rather than writing t wall zeta minus t wall zeta n minus 1, I am going to introduce delta t wall n, which is equal to t wall zeta n minus t wall zeta n minus 1. So this is my representation. So therefore equation 1 can be written as t x comma y minus t infinity is equal to t wall 1 minus t infinity into phi 0 comma x comma y. So this first notation here corresponds to zeta, okay. So zeta equal to 0 plus I can write the rest as summation n equal to 1 to totally n delta t wall n phi zeta n comma x comma y. So the rest of them I am just summing over those n number of discrete intervals, okay. So that I can put under a big summation like this, is that right? So if the temperature variation is not a piecewise constant but actually is something like this, which you have approximated as a piecewise constant, okay. So now I am going to convert this discrete summation into a continuous integral. Okay, that is all I need to do. So for wall temperature variation, which is not piecewise constant, but continuous, so that is either linearly increasing or not linearly, it is continuously increasing or decreasing, you can rewrite this discrete summation as T wall zeta equal to 0 minus T infinity into phi 0 comma x comma y plus integral 0 to x phi x zeta x y. Now how do I write this in an integral? Delta t. So I am going to write this as d t wall by d zeta, which is the dummy variable d zeta. Okay. So all I am doing is I am converting this discrete summation into a continuous integral. So if I have a finite slope and the slope is continuously varying with the location, okay, so all I need to do is get the slope of the wall temperature variation with respect to eta zeta, and that will be used here. Okay, so this is also called as the Duhamels superposition integral. Okay, let us call this as number 2. This is referred to as the Duhamels superposition integral. Okay, so the general superposition which we discussed above is a general method, and usually it is applied where you have this discrete piecewise constant kind of approximation. If you do not make that but directly you put the slope of the wall temperature variation as a continuous variation, if you do that, then the resulting expression is called the Duhamels integral method. Okay, so now once you know the local variation of the temperature, now we can calculate all the other things like the wall heat flux, for example. So now for example in this case we had varied the wall temperature, and now for the varying wall temperature case we want to calculate what is the corresponding variation in the wall flux. The wall flux also varies, right? So it is not a constant anymore, the wall flux also keeps varying with the x location. So we can calculate and write an expression for so the local wall flux can be estimated as, now this is a function of x of course, and that will be written as T wall 0 minus T infinity into h 0 comma x plus integral 0 to x h zeta x into dt wall by d zeta into d zeta, where your h of zeta comma x is nothing but minus k d phi by dy zeta x comma y equal to 0, right? This is my definition of heat transfer coefficient, minus k dt by dy by T wall minus T infinity. Okay, so phi is nothing but your T minus T infinity by T wall minus T infinity. So this is your heat transfer coefficient. So if you differentiate this with respect to y at y equal to 0, you can replace your phi as directly now that minus k d phi by dy as directly h. Okay, now so how do you calculate the local heat transfer coefficient? So already we know for cubic profile my d phi by dy at y equal to 0. What is the value? Minus 3 by 2 delta t. Okay, so also I know the delta t. Okay, so how do I know that? Because delta t is equal to delta into zeta. Okay, and I have got an expression earlier which we derived for the flat plate case with unheated starting length. Okay, so that comes out as 0.976 by Prandtl number to the power 1/3 1 minus, so the unheated starting length there was assumed as x naught. In any generic case where you know the location of the unheated starting length, you can replace that x naught by the z here, the whole power 3 by 4, the entire thing raised to the power 1/3, right. So this was what we derived for flat plate with unheated starting length. So this has to be substituted into this expression to calculate the heat transfer coefficient, and so do you remember how that comes out? Do you remember the expression for heat transfer coefficient that we derived earlier? After we substitute this and also for delta we can assume a cubic velocity profile, and we got an expression in terms of Reynolds number, right. So that and this we substitute into this expression for h, we get a final expression. Do you recollect that? 0.331 k by x into Prandtl number to the power what? 1 by 3 Re power 1 by 2 into one minus zeta by x the whole power 3 by 4, the entire thing power minus 1 by 3. This is what we had derived. Alright. So therefore you substitute this value of h into this expression. Now h is a function of zeta. Okay, so that zeta will tell you what is the unheated starting length for that particular problem. So when you are breaking this problem into multiple boundary conditions, for each configuration you have an unheated starting length. So it starts initially at zeta equal to 0, then zeta 1, then zeta 2, like that you have location of the unheated starting length keep shifting. So that value of zeta has to be used in calculating the local heat transfer coefficient, and that goes into this expression right here. Okay, so that will give us the value of local wall heat flux, which is 0.331 k by x. So this is a constant term which will come out, and the rest of the terms, that is T wall 0 minus T infinity, this is your term, and h, the other terms we have taken out as constant. Now for the very first case, h of 0, there is no unheated starting length, therefore this will be 1, plus you have integral 0 to x. In this case you have the unheated starting length, so there you put 1 minus zeta by x minus 1 by 3 dt wall by d zeta d zeta. Alright, so this is your final expression for calculating the local variation in the heat flux. Alright, so what we will do is tomorrow we will apply this to a problem. I will just do for a simple case where you have a linear variation. What happens if you have a linear variation, then we will calculate the heat transfer coefficient and the local heat flux, wall heat flux. Okay, now what happens now if you have a continuous variation like this, and apart from that if you also have local jumps, something like this. So you have a continuous variation and suddenly you have a jump here, and again you have a continuous variation. So it is what, piecewise continuous. Okay. So in such a case you know the location of these jumps may be at zeta 1, zeta 2, or so the same expression, plus you have to account for these jumps, local discontinuities. Okay. So then your expression for q wall double prime will be h of 0 comma x plus whatever you had before plus what should you do? So this is the same as this, correct? Now additionally you have this local discontinuity. So what you should do to account for that? So once again that becomes locally discrete. So then you have to make this again discrete. This becomes h into delta t. For continuous variation we replace the discrete representation with the continuous thing. Now once you have a discrete jump, once again you will have to replace this integral with a summation. Okay. So summation, suppose you have say k number of jumps. Okay, I am going to go from I equal to 1 to k delta t wall into h, that is it. Okay. So this will take care of both the continuous variation wherever, and wherever you have discrete jumps at these locations you have to write as delta t h and sum them. Okay. So this will give you the local variation of heat flux. So with this we will stop. Tomorrow we will solve an example for assuming a linear variation in the wall temperature, and we will see how to calculate your wall flux. Okay.